Hello and welcome to section 14.6. In this section we're going to see how integrals can be used to measure the center of mass of one-dimensional, two-dimensional, as well as three-dimensional solids. So we'll start with the one-dimensional case, and here you see a picture of a seesaw, and there's a rider off to the left with mass m1 and a rider off to the right with mass m2, and we'll label their distances from this pivot point in green as d1 and d2. And now what's called Archimedes Law of the lever, this says that the system will balance about the pivot if the product m1 d1 is equal to the product m2 d2. Okay, so if you imagine for the moment that the mass of the second rider is relatively a lot larger than the mass of the first rider, then this condition implies that if the seesaw is to balance, the more massive person is going to have to sit a lot closer to the pivot than the less massive person. And if you've ever ridden a seesaw, you'd certainly know that to be true. Okay, so now let's go ahead and introduce some coordinates. So I'll label this reference point here as x equals 0, and then we'll label the positions of the riders as x1 and x2. And then the special balance point we'll label as x bar. This is known as the center of mass of the system. So now I can take this lever condition and rewrite it in terms of this coordinate system. Okay, so notice d1, that would be x bar minus x1, and d2, that would be x2 minus x bar. So that gives us this equation. And now solving that for x bar tells us that the center of mass is equal to m1 x1 plus m2 x2 all divided by m1 plus m2. Okay, so put another way, we're really saying that the center of mass is a weighted average of the x coordinates of our riders relative to this reference point x equals 0, and the weights here are simply the masses of our two riders. Okay, so it's just a certain average of the x coordinates. Alright, now these quantities m1 x1 and m2 x2, these are what we refer to as the moments of the masses m1 and m2, and their sum is what you see up here in the numerator in the expression for the center of mass. That's called the total moment of the system. Okay, and what does the total moment measure? Well, it's a measurement of the tendency of our system to rotate about this horizontal axis through a reference point 0 that's perpendicular to the x-axis. So this axis in red and our x-axis, these lie in a horizontal plane, and due to the force of gravitation, each one of these masses is going to give rise to a certain rotational tendency of the system about this red perpendicular axis. And this total moment here is really measuring the total rotational tendency of the system. Okay, so now with that in mind, okay, I'm going to write the expression for the center of mass now as the total moment of the system, that's what we have in the numerator, divided by, well, m1 plus m2, that's just the total mass of the system. And so now rewriting this, we can say that the total moment is equal to the mass of the system times the center of mass x bar. And the big takeaway from this equation, what this really says is that the center of mass is the point such that if all the mass of the system were concentrated there, this point mass would have the same moment as the entire system. Okay, so over here I've put in this green center of mass point. So imagine taking these two masses and moving them to this location. That new point mass would exhibit the same rotational tendency as the original system. Okay, so this idea of taking some system of masses and concentrating all the mass into some special location, who then will describe the overall behavior of the system just relative to that point mass, that really is the physical underpinning of this idea of the center of mass. And it's an idea we're going to see come up quite a bit as we move through this section. Alright, so now with that in mind, let's look next at a system with n masses. So let's say I have n writers and I want to find this balance point. Well, by a very similar argument, okay, the law of the lever is going to imply that the location of the center of mass is going to equal the sum of the individual moments of all of these masses divided by the sum of all the masses. And I've just rewritten those expressions in sigma notation up here. And so again, we're just saying that the center of mass is the total moment of the system divided by the total mass of the system. Okay, and so if this is how we cover the case when we have a bunch of discrete masses, say along an interval, how would we then go to some kind of continuous setting where I say have a thin metal rod along an interval with some mass density function rho? How could I find the center of mass of this? Well, as is the case with most every calculus question, the idea is to appeal first to the discrete case, which we've already done, and then take an appropriate limit to pass to the continuous case. Okay, so what we're going to do here is just partition our interval, okay, into a bunch of little subintervals, and now for each interval we can approximate its mass by just evaluating our density function at a point in the interval, and I'll call that sample point xi star. So density times the length of the interval, we'll call that delta x. That's going to give us at least an approximation to the total mass of the interval. Now the moment of this interval, so in other words the tendency for this little piece of the rod to rotate there about our reference point at x equals 0, that's going to be given by the mass of the interval, which is approximately just rho times delta x, that's just from right up here, times the position of the interval relative to this reference point. And here I'm just using our sample point xi star to describe that position of our interval. Okay, so now to approximate the center of mass for the rod, okay, we're just going to appeal to what we did up here. We're going to take the sum of the moments, so in other words, take the total moment and divide by the sum of the masses. It's just the total mass. And as we let the number of subdivisions increase, we'll get better and better approximations to the center of mass. So of course now what we're going to do is take a limit. Okay, so as we let the number of subdivisions approach infinity, notice each of these are just Riemann sums, and this top Riemann sum, okay, that corresponds to the integral whose integrand is just x times rho of x. Okay, that's what you see here. And then in the denominator, okay, this is just the Riemann sum for the integral of simply rho of x. Okay, and you can see this parallel now between the discrete and continuous cases in finding the center of mass. And in the next video, we'll go ahead and do some computations. All right, thanks.